anti-jet aircraft, you must understand the structure of vectors and how they work for basic navigation or for weapons delivery. Let's discuss briefly the basic steps for adding vectors. To add vectors in one dimension, we use magnitude sign notation. Angles are not needed. The SIGN is the direction. Distance is a scalar. Displacement is a vector. Scalars have magnitude only, such as volume, area. How many horsepower does your car have? Where vectors have both magnitude and direction. Later on, we will see that force and acceleration are also vectors, as is velocity. Distance is the total path length. This would be what an odometer would measure along this path. Distance does not care anything about the direction. Displacement is the net or total change in position, or the directed straight line distance from point A to point B. Displacement cares nothing about what happened in between, only the starting point A and the final point B. If the position of a body along the x-axis at time 0 seconds is x of 0 seconds is minus 2 meters. 1 second is x of 1 second is 3 meters. And at 2 seconds is x of 2 seconds is minus 6 meters. What is the distance traveled? E. What is the displacement? A. The distance is the total path length, the magnitude of the changes in position. For the first leg, where we went from minus 2 meters to plus 3 meters, the change in position is 3 meters minus a minus 2 meters, or 5 meters. Magnitude of 5 meters is just 5. The second leg, the change in position, is final minus initial, or minus 6 meters minus plus 3 meters, or a magnitude of minus 9, which is plus 9. This gives us a distance, or a total path length, of 5 plus 9, which is 14. The unit is meters. B is the total displacement, the sum of the individual displacements. S1, or the first leg, minus 2 to plus 3, plus S2 from plus 3 to minus 6. Displacement 1, final minus initial position, is 3 minus a minus 2, or plus 5 meters. Second leg, final position is minus 6 minus a plus 3 meters, that is minus 9 meters. Gives a total displacement of 5 plus a minus 9, or minus 4 meters. Summarizing the last example, we have that the total displacement is the first displacement, or S1, or change in position 1, plus displacement 2, or change in position 2. First displacement, or change in position, is the final position minus the initial position, or 3 meters minus a minus 2 meters, plus change in position 2, or final position minus initial position, or minus 6 meters minus a plus 3 meters, giving us a total displacement S of plus 5 plus a minus 9, or minus 4 meters. Notice that graphically the vectors are drawn tail to tip. This is the first displacement, this is the second displacement. Notice that the total displacement is the vector from the first tail to the last tip, or minus 4 meters. So the point is, when vectors are placed tail to tip, the vector sum is the vector from the first tail to the last tip. Now let's look at an example in 2 dimensions where we can no longer just use the plus or minus sign for a direction. Here we will have to use an angle in any of the 4 quadrants for the direction, which means we will need to use right triangle trigonometry. Cuthbert's motorboat has broken down in a bay where the wind is blowing at 3.9 meters per second from the south or towards the north, as shown here. The current is moving at 1.4 meters per second at an angle of 27 degrees north of west. What is the resultant velocity vector of this boat over the bottom of the bay? We have drawn the wind vector and the current vector tail to tip. Therefore, the resultant vector, or R, the sum of the wind vector plus the current vector, is graphically depicted as the vector from the first tail to the last tip, as shown here in red. The x component of the resultant vector, or r sub x, is the x component of the wind vector plus the x component of the current vector. W sub x, or the x component of the wind vector, is 0, since the wind vector is totally towards the north and has no horizontal component at all. The x component of the current vector is plus or minus magnitude of the current, which is 1.4 meters per second, times a cosine of the reference angle, where theta ref is the 27 degrees north of west. Substituting, we see that this x component of this vector, the current vector, is negative. It's parallel to the negative x-axis. So we have minus 1.4 meters per second times a cosine of 27 degrees, which is minus 1.25 meters per second. We carry 3 significant figures here, since this is a 2 significant figure problem and we don't want to propagate round-off error. Let's examine the details of how we calculated that the x component of the current vector, depicted here, is minus 1.25 meters per second. We do that by drawing the tail of the current vector at the origin of a new coordinate system and observing that the reference angle is 27 degrees. We complete the reference right triangle by drawing the x component, c sub x, of the current vector and the y components. The hypotenuse has a magnitude, which is the magnitude of the current, and the hypotenuse is always positive. That's a positive 1.4 meters per second. The cosine of theta ref is the adjacent side, which is c sub x, over the hypotenuse, or the magnitude of c. Solving for c sub x with the sign, not just its magnitude, the magnitude has gone away, is we manually prefix a plus or a minus sign times the hypotenuse, or polar magnitude, c, cosine of theta ref, and so we put in the minus sign because this is negative. 1.4 magnitude of the hypotenuse, meters per second cosine of 27 degrees, giving us minus 1.25 meters per second. Likewise, to find the y component, c sub y, we use the sine function, where the sine of 27 degrees is the magnitude of c sub y over the hypotenuse, or the magnitude of c, or the plus 1.4 meters per second. Solving for c sub y, we manually prefix a plus or a minus magnitude of c, or 1.4 meters per second, times the sine of the reference angle. C sub y is positive, so we prefix the plus sign, and we evaluate 1.4 meters per second sine of 27 degrees, and to 3 significant figures, this is 0.636 meters per second. Now that we have calculated the resultant sum, that is r sub x minus 1.25 meters per second, depicted here, and r sub y, the sum of the y component of the wind vector and the current vector, is plus 4.536 meters per second, depicted here, we can construct the vector sum r, which is the sum of the wind vector and the current vector. Here's the vector from the first tail to the last tip. Its magnitude is the length of the vector. That is the speed of the boat over the bottom of the bay. Theta ref is the direction as measured from the negative x-axis. We calculate the magnitude of the resultant vector, which is the square root of the sum of the squares of the magnitudes of the x and y components. We get 4.7 meters per second. That is the length or magnitude of the resultant vector. We calculate the reference angle, theta ref, the angle between the resultant vector and the x-axis, in this case the negative x-axis, this angle here. The tangent of theta ref is the opposite r sub y magnitude over the adjacent r sub x magnitude. But we want the angle itself, so we want theta ref, which is the angle whose tangent is magnitude of r sub y, this, divided by magnitude of r sub x, this. And we get that theta ref is 75 degrees. Therefore, we can now say that the resultant vector, the vector sum of the current vector and the wind vector, is 4.7 meters per second, this, at an angle of 180 degrees, the negative x-axis, minus the reference angle, theta ref, giving us an angle in standard position of 105 degrees. So r is 4.7 meters per second at an angle of 105 degrees, or you could say at an angle of 75 degrees north of west. Now that you've seen some example problems, you can work some vector addition problems in your homework.